Okay. No worries. So another test. Yeah. Okay, well, yeah, then welcome again to this session, and thank you to Ben and Tom for inviting me as a lecturer. For those who haven't joined the introduction session on Monday, so my name is Hannah Meyer. I'm leading the working group for remote sensing and spatial modeling at the University of Münster, and my main research focus is the development and application of machine learning strategies in the context of environmental monitoring, especially based on remote sensing data. And this is also the broad topic of the workshop that I would like to give today. So it has the title Machine Learning-Based Maps of the Environment, Challenges of Extrapolation and Overfitting, because yeah, based on recent discussions and based on recent work of our group, I would like to put special emphasis here on different challenges of yeah, extrapolation and overfitting that you often see when you yeah, apply machine learning strategies for environmental mapping. And the workshop is split into two parts. So here now in the first part, I would like to give you some yeah, first ideas into the topic and into the challenges that we find. So this will be more the lecture style of this workshop. But then in the second part, after the coffee break, we will see how we can yeah, apply some of the methods in practice and yeah, go hands-on in R and yeah, explore what we can do to overcome some challenges and how to detect these challenges. And but also, first of all, for everyone who is maybe not yet ready to talk about the challenges, we will start very easy, and we will see how we can train a simple model to make spatial predictions. So we will start yeah, quite with a quite simple example here. Okay, but maybe before we talk about challenges, let's briefly talk about why we might be interested in using machine learning in the context of environmental monitoring. And the background is that in environmental science, we're often interested in spatial and spatio-temporal dynamics of environmental variables, like, for example, climate dynamics or spatial patterns of soil properties, vegetation characteristics, or maybe also occurrences of different animal species. So we're interested in spatial or spatio-temporal dynamics, but now the problem is that the data that we usually have available from fieldwork are only point data. For example, from climate stations, from here, soil samples or soil profiles, plot-based vegetation records, or maybe local animal trapping. So we see here on the map, yeah, typical distributions of such reference data, and we see we have just point samples here, and we have many parts of the area where we don't have any point data or any field samples. So we have many red question marks here, and our question is now, how can we fill these gaps between our reference data? So how can we produce spatial or even spatial-temporal continuous maps of the environment? So this is our key question where I would like to start with. And here, yeah, obviously remote sensing comes into play because remote sensing provides us with information in a spatial continuous way. So for example, when we start with a very high resolution, we can acquire data with UAVs that give us yeah, very detailed information about the environment. We might also acquire LiDAR data, often taken from airplanes, that give us additional information about vegetation structure. Yeah, long satellite time series like the Landsat data and also the Sentinel data provide us with continuous information about the environment. And finally, we can also use data on board on geostationary satellites or we can use data from sensors on board of geostationary satellites that are very interesting when we're interested in highly temporally dynamic processes like climate dynamics or weather phenomena, because they typically offer a very high temporal resolution of yeah, something about 15 minutes. So we see that we have very different options here of remote sensing data that provide us with spatial continuous information. The problem is now that these information that we get from a satellite, from airplane, or also from a UAV are only reflectances in different wavelengths, but initially we don't know anything about the variables that we're interested in yet. So we just get the reflectances in different wavelengths, but this is not what we're interested in, because we want to know yeah, distribution of species. We want to know something about rainfall patterns or yeah, other variables. So the question is now, how can we translate the information that we get from the remote sensing platforms or from the sensors to what we're actually interested in from an ecological perspective. And this is quite obvious how we can do that when we use variables that are directly linked to the satellite signal. Like, for example, vegetation cover. So vegetation cover is something that is quite nicely reflected, or that is quite nicely related to the remote sensing signal, for example, or not for example, but especially here in the visible and near infrared range of what we can acquire with satellite data. So what we can do now is to set up a simple parametric model between our remote sensing data here, the NDVI, that combines these two information on the x-axis, and on the y-axis we have field sampled vegetation cover as a reference, and we see here our different point observations, and we see that there is a clear relationship, a clear linear relationship here between the remote sensing information and our field sampled vegetation cover. So what we can do is to model that relationship here with a linear model, and we can use a regression equation and apply it to each pixel in our remote sensing data set, because the NDVI is spatial continuous. So we have information for each pixel. We apply that equation here, and then we get an estimate about vegetation cover for each pixel that is based here on that linear relationship between the remote sensing information and our field observations. So this is quite straightforward for data or for variables that are directly linked to the satellite signal. But now the problem is that for most variables in ecology, that relationship is not that obvious. So for example, when we think about different biodiversity patterns or rainfall or soil properties and so on, these are usually variables where this relationship is not that obvious as we find it here. But we assume that we might have quite complex relationships that are hard to assess. We might think about that we need different sources of remote sensing data, because it's not that simple that we can just look at the NDVI, but we use have to use different information from remote sensing data. This is a problem. We cannot solve that with simple parametric models. So instead, what we need here are models that are able to deal with complex and nonlinear relationships between our remote sensing data and our response variable. And we are need models that are able to deal with different input variables and different and complex relationships between these variables. And here, remote sensing or machine learning comes into play, because the idea is that we use machine learning to learn exactly these complex and nonlinear relationships between variables. So the basic idea is that we have our response variable here on the one side that we acquired in the field, or that we maybe derived from databases, but these are our ground truth data that are typically just available as point data. And on the other side, we have predictor variables. So these are variables that are available for the entire area of interest. And these are variables that we assume might have a relationship with our response variable. So often these are our remote sensing data, so the different spectral information that we get from satellite data, but these might also be other data sets like climate model, or results from climate models, or elevation derived data sets like slope, aspect, terrain position, and so on. So this is everything that we collect that we think might have a relationship with our response variable, and it needs to be available for our entire area of interest. So now the idea is that we feed response and predictor into a machine learning algorithm. Very often random forest is used here in the field of remote sensing. And the task for that algorithm is now to learn the relationships between response and predictors by itself. And in this way, it should be possible to learn complex and nonlinear relationships between these variables. And then based on the learned relationships, we create a model, and we can then take up that model, apply it to each pixel here in our predictor data set to make spatial predictions of our variable of interest that is based on the learned nonlinear relationships. Okay, and using this workflow has recently used quite a lot to map different environmental variables, even ambitiously on a global scale. So what we see here on this slide are 4 of many more examples. So we see so many different environmental variables that have been mapped using machine learning and remote sensing. So for example, here on a global scale, a map of specific leaf area. So an example of a plant trait. We have different maps of biodiversity variables. This one here shows the abundances of nematodes, so little worms in the soil, in 1 kilometer spatial resolution. You might be aware of this map here produced by Tom, global soil maps, also in below 1 kilometer resolution. This one here, for example, is carbon in the topsoil. Or some of you might be aware of this example here because it has been heavily discussed after publication in Science. A global map of potential tree cover, and derived from that the global tree restoration potential. So you know it. Okay. Yeah, so looking at these examples here and keeping in mind that these are just 4 of many, many more examples where machine learning has been mapped to produce global maps of the environment, we might now increasingly get the impression that machine learning serves as a kind of magic tool to basically map everything and everywhere. But there are also increasingly doubts about the quality of the products or of the maps that have been produced, like that recently led to many newspaper articles and scientific journal articles that question the results. So for example, here published in Die Zeit in German, wenn die KI daneben liegt, meaning if artificial intelligence is wrong, or researchers find flaws in high-profile study on trees and climate, both explicitly addressing the tree restoration potential that we have just seen. Or here, paper published in Nature, scientific paper published in Nature that is questioning the methods in more general, with a nice title, Deep Trouble for Deep Learning. So there's also increasingly a loss of trust in machine learning produced maps of the environment, which might lead us to the question if we maybe have been too ambitious by applying machine learning to map the entire world, and as a consequence, that we have a closer look into the question when and why these models might fail in making reliable spatial predictions. And to answer this question or to approach this question, we can start with having a look into what these global maps have in common. And to do that, we have here a look on the reference data that are used to produce the global maps that we have just seen. So in the first one, we have soil maps, and we have plant trait specific leaf area. And in the third example, we have the nematodes data set, so the worms in the soil. And we see here in red the sampling locations that have been used to train the models that are then used to produce the global maps of these variables. And in blue, we see the area for which predictions are to be made. So this is the area, the entire land area, the entire global land area. So this is our study area. We want to produce a global map for the entire world. But to do that, we just have quite limited samples available that are, when you look at that, also highly clustered in geographic space. So we don't have a nice distribution here, but heavily clustered reference data points. And this is also confirmed when we look into these nearest neighbor distance distribution plots here. Look at them closely because you will find many more of these examples in the next slides. So what we see here is a nearest neighbor distance distribution of the data set that we see here. So what we see in red is the distribution within the reference data. So we see here how far away a reference data point is to its nearest neighbor. So for example, here for specific leaf area, this is on average, something like 3-4 kilometers. So each reference data point is 3 to 4 kilometers on average away from a nearest other reference data point. What we see here in blue is the nearest neighbor distance distribution for the prediction area. So this shows how far away a prediction location is to a nearest reference data point. So we see here that on average, we need to make predictions for locations that are 1,000 kilometers away from a nearest training data point. So this shows that prediction actually requires here that we make or that we apply the model to areas that are far beyond the reference data. So we have a data set where data are all quite close together, but prediction, so to produce that global map, requires that we apply the model to areas that are quite far away from our reference data. And this is something that we find,
This is on log scale, right?
It's for visualization purposes, because even worse because otherwise you would, this is just so small, so you couldn't visualize it, So good point. So it's even worse than it might look like. So have a eye on the scale here. Different scale on the next slide, because this is something that we find not only for global applications, but we find the same patterns also for regional applications. So when we might have the aim that we want to produce a land cover classification for this small forest patch here. This is a so-called Marburg Open Forest, a research site of the University of Marburg. And our aim is to produce a land cover classification for that. What is typically done to produce land cover maps is that we use as reference data here training polygons. So these are digitized polygons of known land cover types. You see the labels over here. And our idea is now that we use them as a baseline to train a machine learning model to learn relationships between these reference data and spectral information from an aerial image in this case. And the idea is that we want to apply the model then to make predictions for this entire area here. And here we see exactly the same pattern. Of course, here very different scales. So we're here in a range from 1 meter to 150 meter, but the same pattern. So the reference data are quite close to each other. So we have a highly clustered reference data set, but prediction actually requires that we apply the model to areas that are further away from the reference data. And this is something that most machine learning mapping studies have in common. And the question is now if this clustered pattern causes problems for the classification or for the prediction in general. And this is something that we want to explore on the next slides at this example here. So we use the example here of a regional land cover classification before we go back to more large scale examples and see whether this clustered pattern here might cause problems during our model training process. Yeah, so feel free to interrupt me whenever you have questions in between. Otherwise, we start with this case study example here. So I already introduced you to our reference data set. So we have here our clustered data, so the polygons here that we use as input to train a model. And of course, to train a model, we also need predictor variables. And what we use here are some spectral information, so reflectance in the green channel. We have here visible vegetation index. These are just examples. We also had blue and red, but we're not showing that here. So the green channel, visible vegetation index, we have some texture information like the standard deviation of the first principal component of our spectral variables in a 9x9 pixel environment to bring in some information about the surrounding spectral properties. And what we also use here is the elevation of that forest area here. And what we also use here are latitude and longitude. So these are variables that have been often suggested by authors to improve the prediction performance of machine learning models. I already promised that I will come back to that because it might not be such a good idea to include them as potential predictors. But the general assumption is that the machine learning model that we're going to apply now, a random forest model, is able to deal by itself to sort out whether variables are important or not. So our first assumption might be, well, we just collect everything that we get from that forest area, feed it into the machine learning model, and it will sort that out by itself to find out which of these variables are important, which ones are not, and how the relationships between these variables and our response variable might look like. So let's keep it like that. We feed predictors and response into a random forest algorithm here because it's the most frequently applied one in the context of remote sensing based monitoring of the environment. And based on that, we can produce our land cover map. But such a land cover map is, of course, only valuable when we know the error of the map and if this error is acceptable. And therefore, our question is now, how well can we model land cover with this approach here? Okay, to do that, we apply state-of-the-art validation strategies here. And when we do that and validate our land cover map, we get the following results here. So we have an accuracy of above 0.99, and we also have a kappa value of above 0.99. And keeping in mind that the maximum value that we could achieve for kappa and accuracy is in both cases 1, we could talk here of a nearly perfect prediction model, and we might assume that we can now go on and publish these results with good conscience because we validated them with well-known procedures, and we apparently obtained quite amazing results here for our classification model. However, when we have a look on how the prediction patterns look like, it doesn't seem to be quite that perfect. So we have here our classification that corresponds to our accuracy and kappa value of nearly 1. And for comparison, we have here again the RGB composite of that forest site. And we see already on the first site on the first look, without going into details, that doesn't seem to be a convincing classification model. So what's quite suspicious here is this clear linear cut between predicted grassland and beech forest. We see here in the RGB composite a forest patch that is obviously misclassified as grassland here. And also this round-shaped patch of predicted Douglas fir seems to be quite suspicious. So all in all, that doesn't look like a perfect prediction model. The question is now, how is that possible? Because the statistics just told us we have a perfect prediction here, perfect classification, but now we see patterns that are very obviously not perfect at all. And to understand what happens here, we can have a look on the way how we assess the prediction performance. So you might already heard about that during the presentation of Patrick. I assume he talked about similar things, but yeah, then you will already have an advantage to understand that now. So what we see here is a part of the study area. So we zoom in here into the location of 3 polygons, one overlaid on a cropland, one on a grassland, and one on a road feature. And the type or the way how we assessed the prediction performance was a cross-validation strategy, which is usually used to assess prediction performance. And what a cross-validation in general does is that our training data are divided into several folds, and then we repeatedly train models by always leaving one of the folds out, not using it for model training, but we use it to test the performance of our trained model. And we do that several times until each data point is left out once. So we always keep one part of the data out and yeah, train our model on the remaining data and test the performance for data that have not been used during model training. Okay, and now the type of cross-validation that was applied here, which is still the most commonly applied cross-validation strategy, is a so-called random cross-validation. And what a random cross-validation does is to randomly divide the training data into folds. And keeping in mind that each polygon here that we use contains a quite large number of pixels that might be potential training pixels, we could imagine that a first random selection might look like this. So in this case, all pixels in the polygons are used for training except for those that are marked here in red. So these data points are in a first iteration used to test the performance of our model. The same happens with a second run, with a third run, and so on, until each data point is left out once and is used to test the performance of the model. And I guess you can now already see the problem that we have here now, because by randomly dividing our data into folds, it is now most likely that in each of the folds there are data from each training polygon. And in this way, we can now make statements about how well our model performs on very similar locations. But this is actually not what we want to know, because what we want to know is how well our model is able to make predictions for areas that are on average 100 meters away from a closest reference data point. So what we just done with a random cross-validation that you see here in blue is that we produced prediction situations during cross-validation that are comparable to our reference data set, because if we take a random subset of a clustered data set, we still have a clustered data set, and therefore we still have a distribution here that is comparable to our training data. And with this random cross-validation, we were not able to test the ability of our model to make predictions for new locations here. But this is actually what we want to know, because we want to know how well our model is able to fill the gaps between the sampling locations. So we want to know how well it is able to produce a land cover classification, for example, for this part here of the forest where we don't have reference data. And this can very obviously not be achieved by a random cross-validation, because this is not what we're testing with a random cross-validation. We're just testing how well we can make predictions for nearly identical locations here. And therefore, what we need are spatial cross-validation strategies where we testing how well our model is able to make predictions for new spatial units. And there are many, many suggestions of different spatial cross-validation strategies. And one simple strategy might be a spatial block approach, where we divide here our study area into spatial blocks. And then we perform a cross-validation again, but this time not randomly, but by always leaving data from one spatial block out. I guess Patrick already introduced that in the previous workshop, I assume. Yeah, okay. So yeah, the idea would be that, for example, in this first selection or in that first iteration, we leave all data that are located in this fold here in this block out for validation, and in a second with this block, and so on until each spatial block is left out once and is used to validate the model. And in this way, we are now able to test the performance of the model to make predictions for new spatial units. So we see here again the distribution for the random cross-validation and for comparison here with this spatial block approach. And we see that we produce here prediction situations in blue during cross-validation that are quite comparable to what is required during prediction. So this is quite comparable to our nearest neighbor distance distribution for the prediction area. To any point, so the distance to the nearest reference data point. So, for example, if I for this data point, probably this one is the closest reference data point, so it would be this distance here, and you do that for each pixel, and this is what you see here in this plots. So, on average, we need to make predictions for areas that are roughly 100 kilometers away from a reference data point. But of course, there are also some pixels that are just next to one of the training polygons. And these are those that are quite left here to the distribution, so very small distances. And this is what we need to do when we create that land cover map, because for some pixels are just very close to the reference data, some are far away. And on average, we have this distribution here.
This is based on only the distance, so in the future.
Yeah, we come back to that later. For now, that's only geographic distance. So just, Okay. I hope I could convince you now that the spatial approach might be a good idea. And I guess Patrick tried to do that as well. However, it might be surprising that this topic is then still under discussion, which might be reflected here by this paper that has been recently published with a quite provocative title, Spatial Cross-Validation is Not the Right Way to Evaluate Map Accuracy. And the question is now, what might be the reason that spatial cross-validation might indeed, in some cases, not be the right approach? And to understand that, we can have a closer look into the prediction situations that we just created, because what's quite interesting to see is that with this block approach that we just produced, we actually create prediction situations that are harder than what is required during prediction. So on average, we're testing how well our model is able to make predictions for locations that are, 150 meters away from a nearest reference data point, but prediction requires that we have on average here predictions for areas that for new locations that are like 90, 100 meters away from a reference data point. So we produce here prediction situations that are harder than the actual prediction task. And therefore, I think that indeed spatial cross-validation or this spatial block cross-validation might not necessarily be always the right approach to evaluate the map accuracy, but random is very obviously not either. So instead, I would like to rephrase the title into spatial and random cross-validation is not always the right way to evaluate the map accuracy. And instead, what we need is that we produce prediction situations during cross-validation that resemble those encountered while predicting the map from the reference data. So what we want to produce during cross-validation is a distribution of prediction situations that is comparable to this green curve here. So we want that these two curves match so that we're testing during cross-validation exactly in terms of geographic distance at that point, what is required during prediction. Patrick is there as well. I didn't see you earlier. Okay, so this is our aim now, and yeah, there are several ways to do that. So one suggestion, or not one suggestion, or the way how we could do that is, of course, the trial and error way. So we can try different versions of spatial cross-validation strategies. The MLR3 package, the spatial extension, implements quite many different suggestions. We could play around with the block size. So now I just set it to, I don't know what it was, like maybe 50 meters or so, but we could play around with that, try smaller blocks, larger blocks, until we get a distribution that is comparable to our prediction situation here. So this is something that we could do, and probably that would be possible to do that. Or what we can do is to try the approach that we recently suggested, and that is led by Carlos Mila here, that is called a nearest neighbor distance matching leave one out cross-validation, that has exactly that aim. So we want to produce prediction situations here during cross-validation that resemble those encountered while predicting the map from the reference data. So long name for that cross-validation, the abbreviation that we use is NNDM, for nearest neighbor distance matching, leave one out. So this is a suggestion of how to match these two curves, so to produce prediction situations during cross-validation that are comparable to what is required. And as the title here of the paper already says, it's a kind of leave one out cross-validation. So to briefly describe it, we have here some training samples in this model domain, and we have here a prediction grid. So the aim is to make predictions for this entire area here. And what is then done during this cross-validation is that in each iteration, only one data point is left out, like a leave one out approach is doing. But in contrast to a normal leave one out approach, not all other training data points are used to train the model. So we see here in dark purple a data point that is held back during an iteration, and in light purple we see data points that are completely excluded from the training. So the idea is that we do it that way so that over all these folds, the distribution matches the distribution that we have to look at when we produce the map from the reference data. And we see that for this example here, this is indeed the case. So we have in black here the nearest neighbor distance distribution for the prediction area, and in yellow, the one that we create during cross-validation. And we see that this is quite comparable. So in this way, we produced here or we produce prediction situations during cross-validation that are comparable to our prediction task. Yeah.
Question, and how do we choose how much codes we are making? So here it's the K10. So
here it's very easy to answer because it's a leave one out approach, and if we have how many 10 data points, we have 10 folds. For the other, it's not that easy to answer. So typically, or what is often done is a 10-fold cross-validation, sometimes 5-fold, but this seems to be quite arbitrary how to set these number of folds. What we could do here, for example, if we go back to the block approach, which might be an idea, is that we do a leave one block out cross-validation, which would then end up here with 20 folds. So this is could be something we could do, but there are no general rules as far as I'm aware of how many folds we create. But here for the leave one out approach, it's very obvious how many we have, because we have as many folds as we have data points, and this already might ring a bell for some of you. So this will be a cross-validation strategy that runs for a while, because it makes a difference if you have a 3-fold, 5-fold, or 10-fold cross-validation, or okay, in this case it's just 10-fold, but if we go back to some data sets where we have maybe like 20,000 reference data points, we would train a model 20,000 times, and this of course runs for a while. So in this case it might be a better option to manually try to adjust the spatial units or spatial folds to create prediction situations that are comparable to what is required. Okay, but what we see here are the results of this nearest neighbor distance matching approach for two very different sampling designs. So we have here, I don't know if you can see it, but we have here a clustered design. So sampling points that are clustered in geographic space, large gaps in between them. And we see the sample to sample distance is quite small because each reference data point has a neighbor just a few kilometers away. But prediction requires that we apply the model to areas that are like between 1,000 and 10,000 meters away. And we see here in blue the prediction situations that we produce during this cross-validation. And we see that this indeed matches quite nicely the distribution that is required when predicting the entire area. And we see the same for random distribution here. So in case of a random distribution, the sample to sample distance is comparable to the sample to prediction distance. So there's not much of a difference. And also our spatial cross-validation, not our nearest neighbor distance cross-validation, which is not spatial in this case, produces something similar, because in this case, probably no data point is excluded during training because it would try to achieve exactly that distribution here. So this would probably end up with a simple leave one out approach where not much needs to be excluded to produce this distribution here. And we see in this figure here that this approach seems to be indeed a good indication for the true map accuracy, because what we see here on the y-axis is the difference between the true map accuracy and the cross-validation estimate for a simulated study. That's why we know the true map accuracy. And we have here on the x-axis different sampling designs, so regular sampling, random sampling, and then we have clustered designs, and we have in color the different cross-validation strategies. So here simple leave one out approach that produces results that are comparable to a random cross-validation. We have a spatial block approach in yellow, and we have in blue the newly suggested nearest neighbor distance matching approach. And what we see, which is not new, is that the leave one out approach, which is comparable to the random cross-validation, heavily underestimates the error when we have clustered reference data, while the spatial block approach might produce overly pessimistic results here when we have random or regularly distributed reference data. And what's nice to see in blue is that the new suggestion here seems to produce quite good results regardless of the sampling design. So regardless of the sampling design, we are always here very close to the 0 line, which indicates that we have no difference between the cross-validation estimate and our true map accuracy. Okay, so let's come back to our case study. I hope you still remember it after talking so much about these cross-validation strategies. So we stopped at that point before we went into the discussion about the different strategies at that point, where we had this random cross-validation of that led to accuracy and kappa values of 0.99. And we were wondering whether we could call that a perfect prediction model. And I think now very obviously the answer is no, or we don't know, because we didn't validate our model in view to what it needs to achieve. So we didn't validate the accuracy of our produced land cover map. And what we need to do is to assess the map accuracy by a suitable cross-validation strategy, which might be any kind of cross-validation strategy where spatial units are held back and where the distribution or the prediction situations that we produce during cross-validation are comparable to what is required when we produce our land cover map. Okay, and when we now do that and apply such a strategy on our case study model, our results change quite considerably. And now our spatial approach led to accuracy of 0.68, and also our kappa value dropped quite considerably. So apparently our model was less able to make predictions for new spatial units compared to what we would expect if we just consider here the random cross-validation estimate. And that, of course, now looks much more negative. So we don't want to see results like that. We always want to achieve results above 0.99, of course. But this is, this random cross-validation strategy doesn't tell us anything about the ability of the model to make spatial predictions. So we don't know anything about the map accuracy here, which we can only estimate if we use a cross-validation strategy here that is appropriate for the prediction task. So we could now conclude at that point here that standard validation procedures lead to an over-optimistic view on the prediction performance, and instead prediction situations created during cross-validation should resemble those that we encounter by predicting the map from the reference data. And that this topic is still underestimated even in the community is also reflected by the editor comments of a paper that we once published where we applied spatial cross-validation strategies that said, I'm actually surprised to see the poor performance of your neural network approach. Typically, with sufficient training data, a neural network approach can often reproduce a predicted variable very well, even if the underlying reasons are unknown. But this is now exactly the point that we want to make here, because to reproduce data is not the same as making spatial prediction. And when we have clustered reference data and we apply a random cross-validation, we're only testing the ability of our model to reproduce the training data, but we're not testing the ability of our model to make spatial prediction, which we can only achieve when we apply a spatial cross-validation that is aligned with the difficulty of the prediction task. However, we agree with the editor in one point, and this is that the prediction doesn't seem to be quite convincing. So we can now change the validation strategy to the most appropriate one for our prediction task, and therefore get a more reliable error estimate. But changing the validation strategy itself for error estimation or for performance estimation doesn't change the model. So now we can get a better estimate for this land cover map, but still the land cover map is not really what we want. So we didn't get rid of these obviously wrong prediction patterns here. So the question is now, what can we do to improve this prediction performance? And the answer is quite obvious when we follow the XKCD recommendation of what to do in this case, because what is recommended here for the point that we have a machine learning model that produces the wrong answers, but what we do is we just stir around in our pile of data and shuffle things around and around until at one point they start looking all right. And although that might indeed be a solution to our problem, and if we do that long enough, we maybe at one point end up with something that is looking convincing, but this is obviously not what we want to do in order to achieve scientifically meaningful results. So we should probably start our search somewhere else of what to do to improve our model. And we should probably start our search by trying to identify where these prediction patterns actually come from. So what drives these prediction patterns? Why do we have these weird linear cuts in our prediction? So where does this come from? And we can start our search, or obvious start for that search might be to have a look into the variable importance ranking of our random forest model that is telling us here in decreasing order of importance the relevance of our variables. So we see here which variables are mainly responsible to drive the prediction patterns. And this is obviously longitude, latitude, and elevation. So these are the variables that are mainly responsible for the prediction patterns that we have just seen. What these three variables have in common is that they feature a very high spatial autocorrelation, which means that the values for these three variables are quite comparable within the clustered reference data. So each of the training polygons has obviously similar values for longitude and latitude because they're just located at more or less the same latitude and longitude. And also elevation features a high spatial autocorrelation. So this is what these three top ranked variables here have in common. And when we critically think about it, it's actually quite unlikely that latitude, longitude, or elevation are really variables that are responsible for land cover patterns for such a small forest area. So instead, we might suspect here that the spatial dependencies lead to confounding information and that the true relationships are not recognized, which might cause the model to fail in making spatial predictions. So what we could suspect here is that our model is behaving like the clever Hans. So Rebana already introduced you to the clever Hans in a previous lecture. For those who haven't been there, so the Clever Hans was a horse that lived around 1900, and it got famous because it was apparently able to solve even complicated mathematical equations. So whenever the owner of the horse showed two numbers to the horse was able to sum up these numbers, and then he tapped his hoof as many times as needed to indicate the right answer for this question. And this was certainly quite a sensation, but it was later found out that the horse was just reacting to some unintentional body language of the owner. So he has not gained any understanding of numbers or has gained any understanding of solving equations, but he was just reacting to some confounding information. And as a consequence, he could also not generalize its skills because he has just simply not gained an understanding of what is required here. And this Clever Hans effect recently also found recognition in the context of deep learning-based image classification. So if we stick to horses here for another slide, here in a recent publication, Nature Communications, the authors have been impressed by the high ability of a model to detect horses in images or to identify images of horses. So they wanted to know, if you look at that image here, what is the information that the algorithm uses to detect a horse? So what they did is they looked into the heat map that is showing the relevant parts of that image, or this part of the image that is mainly responsible for the model to make the decision that this must be a horse. And what we see here in red is that the most relevant location is this location here of the image where source tag was present. So apparently the source tag was responsible for the model to make the decision that this must be an image of a horse. So obviously, what happens if we remove the source tag from the same image? Well, the source tag is not there anymore, so the model loses the ability to realize that this must be an image of the horse. Of course, this is quite dangerous because what happens if we artificially insert a source tag to an image of something else, like here, image of a car? Well, a source tag is there in the left corner, so the model has learned if a source tag is there in the left corner, this must be an image of a horse. So as a consequence, this image here would be classified as a horse image. If you remove the source tag again, the information is not part of the image anymore. And as a consequence, this image would not be classified as a horse. So this is an example here where apparently the model is right, but for the wrong scientific reasons, because it didn't even look at the object. It didn't even look at the horse, but apparently it produced the right answers. But as soon as the settings change, so if we confront the image with the model with images of horses that maybe come from another database where no source tag is present, it will not be able to make any reliable predictions, because if the scientific reasons are not right, the model won't be able to make predictions for new samples because it simply has not enabled to learn about the relevant relationships here. So the question is now, what does it mean for our case study, so for our land cover classification task here? Well, we already revealed by spatial validation that our case study model is not right because it was apparently not able to make predictions for new locations. But the question is now, how can we make it right? So what can we do based on what we have just learned to prevent the Clever Hans effect and to produce more reliable classifications here? Well, if we assume that longitude, latitude, and elevation due to the spatial autocorrelation lead to the Clever Hans effect because they act as Clever Hans predictors and don't bring in relevant information here, or if the model cannot really learn relevant information from these variables, well, then the solution is rather simple. If we remove these variables from the model, in theory, this should improve the prediction results because we just remove the information that cannot be interpreted by the model. So what we therefore need to automatically test for that is a spatial variable selection that is testing which potential predictor variables have a meaning, so which ones are relevant to make predictions for new spatial areas, and which ones either have no meaning or are even counterproductive because they act as Clever Hans predictors. And to do that, we implemented a variable selection strategy into the R package cast that is exactly doing that. So it's testing which variables are relevant for spatial mapping and which ones are not, and might even be counterproductive. And if we apply it here to our to our case study, we see the results here in decreasing order of relevance, and you only need to look at the labels here. And when you look at the labels, so these are the variables that have been selected, all other have been removed, and we see that neither latitude nor longitude nor elevation occur here anymore. So apparently they have been identified as either having no meaning or as being counterproductive because they produce or due to the Clever-Hans effect cannot be reliably used to make predictions for new spatial units. Okay, and if we now only use the selected variables that have been identified by the spatial variable selection strategy to have a relevance, we see that our prediction patterns now change quite considerably. Without going into detail here again, we got rid of that clear linear cut that could be clearly traced back to misinterpretation of longitude in our model. Also that round-shaped patch of predicted Douglas fir is not here anymore, which could be traced back to a misinterpretation of elevation in our model. And also this forest patch here is now predicted as spruce forest. So we could also improve the classification model for this part of our study area. Okay, so what we have learned so far is that cross-validation strategies affect the performance estimate. They affect selected hyperparameters. We didn't talk about that now, but I think Patrick talked about that in a previous session. At least there's a paper about that, where you can see that the selection of the cross-validation strategy also has an impact on the hyperparameters. And what we talked about a lot is that cross-validation strategies affect the variable selection here. So what we have seen that the consequence of using an unsuitable cross-validation strategy is that we are not only getting unreliable performance estimates, but that we might also produce models that can well reproduce the training data, but might not necessarily be meaningful or good models to make spatial predictions. So as an example here of the Clever-Hans effect. And therefore, cross-validation strategies that fit the prediction task are required during model selection and validation. And now I would like to give you a few, or maybe not advices, but maybe guide you through some ideas how this, what we just discussed, might be helpful for the spatial prediction competition. So how can we use this information to maybe produce a successful submission there? I hope that's not against the rules, but I don't think so. Because I'm not going to talk about the spatial prediction competition for this year, but I want to quickly show you some results of the spatial prediction competition of 2014, where I participated in that year and where my strategy was apparently a good strategy to produce spatial predictions. So the strategy or the prediction task in that year was the following. So we had here a small farm, the so-called Cook farm, and on that farm several sensors had been installed that recorded soil moisture and also other variables continuously, I think for 5 years or so. I think Ben also knows more about that. Or knows exactly the same as I do. Yes, for several years they recorded these parameters here, and as predictors, the task was completely open, so it was up to us to decide for predictor variables. So with the data set, we also got an elevation model, soil properties, rainfall, so climate variables, and so on, which could be used as potential predictor variables. To give you a short idea about how the data set looked like, we have here our roughly 40 reference data points. So these were the sensor locations, and each of these locations produced a time series. So for each locations, we have measured, in this case, soil moisture here from, I don't know, so it's showing that from March to April, but the time series was longer. So we see that behind each of these locations, we had time series of measured soil moisture. And the aim was actually to produce 4D predictions. So we want to make predictions in time, in space. So you see here predictions for the entire Cook farm, and also in depths. So for different depths of the soil. So you see here some results that we published afterwards in 2014, where you see spatial predictions. So in yellow, you have areas that apparently had a very little soil moisture, and with increasing intensity of blues, we have predicted moisture conditions for these areas here. So that was the background of that prediction task. This was what we should, or that was the task that we should had to achieve. And now to introduce you to the winning strategy, which was the following. So as potential predictor variables, what I chose here was altitude. Altitude was the depth of the soil because we had 4-dimensional data. I had the year because we had several years of training. I had the day of the year. So from, for each year, a number. These were some soil properties. I had latitude, longitude, elevation, topographic wetness index, and so on and so on. I just highlight these two here, latitude and longitude, because I just made you aware of this that this might be quite dangerous to use as predictor variables. And what I did is to train a random forest model with random cross-validation and use that model and to make prediction for the test areas. And now my question to you would be, why do you think that these predictors and a random cross-validation for model selection could be a successful strategy? So I chose a random cross-validation at that point because I was not aware of any other cross-validation strategies. So it was not on purpose, but it turned out that this was a good idea to use that. And my question would now to you would be, what do you think? So what might be the reason that latitude, longitude, day of the year, and so on, and random cross-validation produced something with which I could win this competition?
Well, one thing that keeps on popping into my head is, well, isn't all of this still a question of scale? For example, I mean, it's like with the example of this and then what you showed with the forest, it's like the scales are completely different. Here, your sample points are on, I mean, at least all things considered, you know, the level, pretty homogeneous area still for all intents and purposes.
Mm-hmm.
Whereas the other one was at a scale where you had, you know, not only just natural influence, but pretty different multiple types of anthropic influence.
Yeah.
So that just keeps on popping into my head. It's like, does that have an impact on how we sampling and at what scale we do this?
Might be, but that's not the point that I wanted to make. But yeah, we should still keep that in mind. Yeah. Yeah. That's right. Yeah, I didn't think about that. Yeah. That's true. Other ideas? Latitude, longitude. No clustered samples is a good suggestion. That's right. Yeah. Yeah. That's another point, but still we want to make predictions for areas of the farm where we didn't have installed sensors. You're right, one of the weak points, Laura, was it would have been better example if these have been clustered at certain locations. They're unfortunately not. Maybe think about the time dimension of the reference data. Well, otherwise, I just show you the prediction task or the data that have been used. So it was again a prediction task where it was winning by number. So the predictions were compared to validation data points that we didn't have, that we got afterwards. And then the true soil moisture was compared with our predicted soil moisture. And when you have a look into these locations here, we see here again some time series with two of the sensors, one here, one there, and you see in black the data points that have been used or that were provided to us to train the model, and in red you see the data points that were used to validate the model. So these were the data that we didn't get and where we were evaluated, or where our approach was evaluated on. So we see this for this location, a second, and so on and so on. And what you can clearly see here is that we did not get new locations for model validation. So we had 40 reference data points, and the time series provided by these 40 reference data points were split into training and test. So we never had to make predictions for new spatial areas in that farm. We just had to make predictions for new points in time for the sensors that we used to train the model. And I think you can already guess that it's quite easy when you have these data points here for training, that if you have a model that is learning from that time series, because you get latitude, longitude, and the day of the year, you can make very good predictions for these data points that are not used for model training, because you simply had all information from the neighboring data points here to train your model. And that's why a random cross-validation was instead a good idea, because what we produced here during cross-validation were distances that were comparable to the prediction task. So you see here this an overlap of the cross-validation distances, the sample to test distance and the sample to sample distance. That's why it occurs in this color here. And the sample to test distances were comparable to what we produced during cross-validation. So we never had to make predictions for new areas. We just had to make predictions for the same locations. While the spatial prediction would actually require that we apply our model to areas that are much further away, because we still have to make predictions for the rest of the study area, but that was not asked during the prediction competition because we only got subsets of the same time series. So here we have an example where our cross-validation fits what was required to win the competition. It did not fit what was required to produce spatial predictions, but it did fit the prediction task, and therefore we also got here high R-squared value 0.91 in this example, and this was very close to the true prediction accuracy, because our cross-validation strategy was quite comparable to or was quite meaningful for the prediction task. And in contrast, if we had chosen a spatial cross-validation strategy, we would have successfully evaluated how well our model is able to make predictions for new locations. And this would lead to lower R-squared values, so here only 0.39. So the model was less able to make predictions for new spatial locations. But again, since this was not asked during the validation, it didn't matter. So at that point, it was really a good idea to use latitude, longitude, and day of the year as predictors, because what we actually did is to produce a model that was heavily overfitted to the training data. But as long as the validation data ask exactly for that, that might be a good strategy. And this shows you that you should, as an advice, train and validate your model with respect to the aim of the modeling approach, which might be spatial or 4D mapping. It might also be winning the competition. And this means that you would need to look at the validation data and see what is required to win the competition, and not what is maybe required or what you want to achieve here. So this again as an example where these two things need to be aligned. And in this example, latitude, longitude, and day of the year as predictors was probably a good idea, because with this we could perfectly reproduce the time series, but probably it would not have been a good choice to make spatial predictions. And therefore also in a later version of that, we performed spatial variable selection to produce models that were really able to make spatial, temporal, or 4D predictions, which was obviously not achieved by using latitude, longitude, and day of the year as predictors. Okay, so much for the spatial prediction competition. Now let's come back to the point where we stopped before making that little detour. So we said cross-validation strategies that fit the prediction task are required during model selection and validation. And if we take that into account, we can now produce models that are best able to make spatial predictions, and we can evaluate our models in a way so that we get estimates that are close to the true map accuracy. But the question is if this is sufficient for reliable mapping or even global mapping, because what we did so far for global tasks as well as for regional applications is that we trained and validated our models based on the field samples. However, when we look again at typical field locations, we again see they're heavily clustered, and we have large areas where we make predictions for, but where we don't have any training data at all. this means that when we produce predictions for these areas, we transfer the model to a new space, and we assume that the relationships that have been learned based on these field data are still valid for these new locations where we don't have any reference data. However, this new space might considerably differ in its environmental properties compared to the training data, which is something that we, for example, find here in the nematode data set. So we see here, again, nearest neighbor distance distribution, but this time not in geographic space, but in feature space. So we see here the nearest neighbor distance distribution within the training data in red, and in blue what is required during prediction. And again, we see that the data are not just clustered in geographic space, but also in feature space. And that prediction actually requires that we apply our model to areas that are very different in their predictor or feature properties. And now the question is, can we do that? So what happens if the model has never seen such new predictor properties, if it was never trained on such new combinations of predictor variables? And this is not too much of a concern for simple models like linear models here, because we model the relationship between predictor and response based on an assumption about the relationship. So here we assume a linear relationship, here in black, between predictor and response based on our field locations here. And we might assume that this relationship also holds true beyond the range of observed data points. And second, prediction intervals here quite nicely reflect that prediction gets harder when we move away from what we observed in our predictor variable here. However, now there is a good reason why we apply machine learning and not linear models, and this is that we assume that the relationship between predictor and response is not that simple. So we might think about relationships that look like that. So in green here we have a true relationship, a simulated true relationship between predictor and response. In black we have some reference data points, and the black line represents predictions made by a random forest. And we see that here the random forest is very well able to make predictions for areas where we have a good coverage of training data points. But we see that this ability to fit nonlinear relationships comes with a disadvantage. And this is that the models are very weak in extrapolation. So whenever we have gaps here in the predictor space, for example, there, or also here when we come out of the range of observed predictor values, we see that random forest cannot handle that at all. Especially here, when we move out of that range, Tom already showed this behavior here. All trees just make the prediction of the last observed values. And that's why we have this straight line here, because it is just predicting the same value here from this predictor value onwards. What we also see here is that commonly applied uncertainty estimates, like standard deviations of predictions made by the individual trees, are not a good indicator to show that prediction gets harder for these areas. So especially here, when all trees make the same or provide the same answer, the standard deviation is 0. So all trees produce the same result. And that's why these prediction intervals are very narrow here. And we might falsely think that these areas, or that our model is very confident in these areas here, which is clearly not a good idea to assume this. And the question is now, if we cannot make reliable predictions for those parts of the predictor space where we don't have training data, and if we cannot interpret any uncertainty measures to make clear that prediction gets harder here, the question is, shouldn't we better avoid predictions into this unknown space, because we simply have not observed these characteristics, and better present no data values instead, and just simply don't apply our model there? And I think this is something that we should do in order to avoid misleading predictions. And therefore, Edsa and I, as a Corona lockdown project, worked on a method that we called the area of applicability of prediction models, that we define as an area to which the model can be applied because it has been enabled to learn about relationships, and where, as a consequence, the estimated performance of our models hold. To give you an idea about the aim, I can show you here a very, very obvious example. So it's something that should be obvious to everyone. What we have here is a sentinel scene from the Marburg forest again, and we have here's some data points where the leaf area index was measured. It was just measured in trees. It was a study project where the students went into the forest and they measured leaf area index for these point locations here. And yeah, using Sentinel-2 as predictor data set, we might now think about producing a model that is able to make predictions of leaf area index for the entire area. And if we do this and apply it to the entire area, we get predictions for the entire Sentinel scene here. So technically, that's no problem. You will see after the break that is something that is just one line in R, and you have this nice map of predictions here. But the question is now, should we have done so? So should we have provided predictions for the entire area? And if we apply the concept of the area of applicability that I will introduce you to in the next slide, the idea is that we get the following results. We have here again the predictions shown here, but here only provided for the area of applicability. So everything that is gray was identified as being outside the area of applicability. And if you compare that to the Sentinel image, and this is why I said it's such an obvious example here, everything that is not forest area falls out of the area of applicability, which makes a lot of sense because our model just learned from forest locations. And that's why naturally, especially when we use leaf area index as a response variable, we cannot apply the model to anything else in forest because it just doesn't make sense. The model has never seen such spectral properties that we find in urban areas or open soil or even grassland sites. So this is the idea, and to quickly guide you through the method without going too much into detail, what you see here are some reference data points in a two-dimensional predictor space that has been scaled and weighted by the variable importance. So the idea is that some predictor variables are very important in a model, some are not. And if a variable is not important and is not used in a model, then it doesn't matter if we run out of the, or if we have gaps in the predictor space there, or even go out of the range because the variable is simply not used. While some variables have a high importance, and that's why there it's very important that we stay close to the observed values. That's why we weight them here by the importance. So what you see here are some arbitrary training data points in this two-dimensional space. And the first step towards the estimation of the area of applicability is that we calculate the distance between all training data points. That's not the important part, but the more important part is that we then estimate dissimilarity within the training data set. And we do that by taking the cross-validation folds into account. So you see here again the same data points, but this time colored by fold membership. So we have 3 folds here. And if we now only look at one of the data points, so this one here, what we do to calculate a so-called dissimilarity index is that we calculate the distance to a nearest other data point that is not located in the same cross-validation fold. So in this time, this blue point here is the nearest data point, and we calculate the distance divided by the average distance to get what we call a dissimilarity index. And we do that for each other data point. And if we do that, we get the distribution of the values for the dissimilarity index here that you see in that box plot. So for each data point, we get a value for the dissimilarity index. And we now assume as a threshold for the area of applicability, the maximum dissimilarity that we find in the training data, excluding the outliers. So we assume that a new data point is outside the area of applicability if it's more dissimilar than what we observed in our training data set. So we can now apply that to a new data point or to any new data point. For example, if we have, or if we want to make prediction for a data point that has these predictor properties here, and we want to know, is it inside the area of applicability? We calculate the distance to a nearest reference data point to calculate the dissimilarity index, which is 0.92 in this example. We look up, is it above or below the threshold here? It's obviously above the threshold. So in this example, this data point would fall outside the area of applicability. And we can now do that for each pixel in our data set to map the dissimilarity index and to map the area of applicability. And this is what we will do in this example here in this case study. So let's slowly move back towards the larger scale. So from our local application, at least to to the European scale. So what we have here is a simulated example. We will also look at that in the practical session later on. We have here some predictor variables. These are bioclimatic variables for entire Europe, and based on them, we simulated a response variable that you see here. So for this example, we have our spatial continuous reference already, but we want to simulate a typical prediction task, and therefore we select reference data points, and what we use here are heavily clustered data points. So you see here 50 clusters, and each cluster has another, I don't know, I think 10 data points. So this is our reference data set. So to make things clear, we make them extremely clustered here. If we now apply, again, a machine learning algorithm to learn the relationships between the bioclimatic variables and our response variable, we can make spatial predictions that you see here. Spatial cross-validation error, by the way, 0.79. We have here for comparison, again, our reference map here, the prediction, and we see again, technically no problem. We can make predictions for entire Europe. And the question is again, should we have done so or not? And therefore, we calculate the dissimilarity index for the entire area that you see here. And we see here that with increasing brightness, we have an increasing dissimilarity, which is especially the case here for the west coast of Norway or for the Alps. So apparently these are areas that are very different in their predictor properties compared to our training data set. And I think especially for the Alps, it's quite obvious that this is really an area that quite obviously differs in its environmental properties compared to other areas in Europe. Oh, wrong direction. And one is, okay. Again, the slide from the beginning. Now we get the true error, because what's nice to see is that the patterns here in the dissimilarity index also quite nicely correspond to the true error. For this example here, it doesn't need to be like that, but in our case study, it's really nice to see that there is a good relationship between the dissimilarity index and the true error. So apparently in all areas where we had a high dissimilarity, we also got a high prediction error here. So our suggestion is to derive the area of applicability based on a dissimilarity index. And you see here again, these predictions, so exactly the same, but this time limited to the area of applicability. So all areas that are above the threshold are marked here in pink. So these are areas where we say we don't know what happens there. We don't know which predictions or about the reliability of predictions, and we cannot assess them because we never evaluated our model for areas that have such an obvious difference in their predictor properties compared to our training data set. And I want to make you aware of one important aspect, and this is, as I said, that the area of applicability depends on the cross-validation, because we use a cross-validation strategy to derive the threshold. This might look for these examples like that. So we have here again our training data and our predictions produced when using spatial cross-validation, and the area of applicability is that you see in pink, so exactly what you've seen on the previous slide. And we see the same patterns here for random cross-validation, R squared 0.99. So again, this indicates just the ability to make predictions within the spatial clusters. And as a consequence, we also have a very limited area of applicability, because we never produced prediction situations during cross-validation where we were testing the ability of the model to make predictions for new areas, and this time new not in geographic space, but in predictor space. And therefore, these areas where we still have predictions here are most likely those areas, or not most likely, we see it here, that are either the areas where we had reference data or areas that are very similar in their predictor